Hello Uniteds and welcome back to Mathematics. In today's lesson we're continuing with our topic of indices and surds, and we're going to actually look at the final section in this topic, looking at scientific notation. Now, in this lesson we want to be able to understand what scientific notation is and also be able to apply scientific notation to write small and large numbers and also express numbers in scientific notation back in decimal form. So that's what we're going to be focusing on in today's lesson, this scientific notation thing. So let's get started. First of all, we need to talk about what scientific notation is. Now, scientific notation is a way of writing numbers which are very, very large or very, very small. And so what mathematicians and scientists in particular do is they represent numbers which are very, very, very big and very, very, very small using a bit of notation to write it a little bit different to how we would normally write regular numbers. And the reason why this is the case is because some numbers get really, really, really big and it gets really irritating to write a lot of digits, and some numbers get really, really, really small and it gets really irritating to write a lot of digits for those numbers. So for example, to give you an idea of when scientific notation is often used, I've got two little animations, gifs little here, gifs here. I sounded really old just then, didn't I? Two gifs here, just to illustrate two places where scientific notation is used. And we're going to first start off by looking at things that are really, really large. Now, things that are really, really large that use scientific notation is when we talk about distances in our universe. Now, I'm not sure how often you think about this, but out there, outside of Earth, outside of this solar system, there's a whole bunch of planets, stars, and so on, and all the light and universes outside of here, and they're really large distances away. I'm not sure if you've seen that animation before, and I couldn't actually find it, where someone is zooming out from their backyard on Earth and eventually gets really, really far away, and you can't even see the Earth on that in the animation. Those large distances are really hard to describe using the kind of ways that we would normally describe distances. So like when we talk about distances, we might say, oh, I'm going to walk a couple hundred meters, or maybe you might travel like a couple kilometers to the nearest shops within 5 kilometers as it stands. But when scientists refer to these large distances in our universe, they use a different measure called light years. It's the distance that light travels within a year. Light travels at, you might have heard of the phrase speed of light. And so when they refer to 1 light year, they're referring to how far would light travel in a year. And so, for example, 1 light year, it's not for example, 1 light year is set, it's a set amount, and 1 light year happens to be, okay, here we go, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 kilometers. Now, I'm not sure how many kilometers is that. That's 9 million, which I think might be 9 quadrillion. I'm not sure. 9 quadrillion kilometers away. And I'm not sure about you, but as I was writing this, that got a little bit annoying. And so when mathematicians don't want to write these large numbers, and so they actually shorthand it using scientific notation. We'll talk about what that looks like in a moment. So like for example, the nearest star to our solar system is this star over here called Proxima Centauri, and that is approximately 38,000. Oh my god, 38214 1 2 3 4 5 6 7 8 9 kilometers away from Earth. And so it's really irritating to have to write these large numbers. And if you're reading a paper or if you're reading some sort of facts about distances between local stars, you might be like, oh my gosh, this is really irritating. Is there a much easier way to write it? And so scientists and mathematicians actually use scientific notation to write big numbers like these ones, which represent distances in our universe, for example. The other place where you sometimes might see scientific notation used is for really, really small things. Now, here is a little animation, the first animation I could find when I searched up our favorite phrase of the year, word of the year, coronavirus. And so virus cells, I'm not sure if we can really call them cells. You can ask a science teacher about this. But virus cells are actually really, really small. One of these cells have the diameter, and I can't draw on top of this. One of these cells, the diameter of one of these cells is approximately 0.000 0.0000002 meters. And so we don't like to write these kind of measurements. It's very, very, very small. So sometimes you might see them actually write this. This is actually equal to 20 nanometers, which is a little bit easier to write. But big, very small numbers like this also, we don't like to write really small numbers. And so the same kind of notation that we use for these large numbers and will also work for these small numbers. And so scientific notation is a way that we can write these large numbers, like the distances in our planet, and also these small numbers, like the size of a virus cell, in a really easy to read way that represents how big or small a number is. So what is scientific notation? Scientific notation looks a bit like this. So when we want to write a number in scientific notation, it will look like this: a times 10 to the power m. A times 10 to the power n. Now this has two parts, and I've highlighted the two parts. This is number a and this is number m. And so let's talk about a first. A is just tells you what the measurement is. And so a is the measurement. And it is a number between 0 and 10. So a has to be between 0, I think, is it 0? No, it's 1 and 10. Whoops, my bad. Between 1 and 10. And so this is how that number at the beginning of your measurement. So for example, for the distance from Earth to Alpha Proxima Centauri, it would be that 3 here. 3.8214. And so here it's a number between 1 to 10. This is the first part of our scientific notation. So this tells us about that measurement. What is that measurement talking about? The m here at the end, so the m value, this is the magnitude of 10, magnitude or power of 10. So it tells me how big that number is. How big that number is. Because if you remember, when we multiply by powers of 10, you can just move the decimal point left or right. And so here, by shorthanding it using this times 10 to the power m, we can just tell, it tells us where that number, where our particular measurement is. And it tells us if it's very big or if it's very small. And so the way that we can tell this is, if this is the case, is we check the value of m. So if m is positive, so if we've got a positive number, that means that we have a very large number. So for example, we'll go through actually the two examples up above. Or if it's negative, that means it's a very small number. So m just tells us the power of 10, and it just means where our measurement is. Now, whether or not it's a big number or a small number. Okay, now the other thing here with a is usually the way that we can, I forgot to add this on, when we write down the value of a, we usually just put, we take the first digit of our number and place decimal point after it. So those examples that we had to look up above, we said that the distance from Earth to the nearest star was 38214,000,000,000,000,000. If we were to write this in scientific notation, this would just be equal to, I take the first digit, so 3.8214. So here, if you have a look, this number here, that's my value of a. And this is a number which is between 1 and 10. Great. And all I did was I took the measurements here and I just put a decimal point after the first number. And then I need to multiply that by a power of 10. And the way I do this, I just count from here at the back. That's where the decimal point would be. And I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And so here, this is 2 times 10 to the power 13. So that's how I would write this big number using scientific notation. The other one example that I gave was with that really small number for coronavirus. So here 0.0000002. And so here for this one, this would just become, well, the measurement here, the number that I have here is 2. So it'd be 2 times 10 to the power, and I have to move this decimal point 1, 2, 3, 4, 5, 6, 7, 8 times to get over here. So this is times 10 to the negative 8. So that's what this scientific notation looks like. Now, what we're going to need to be able to do into this lesson is to be able to write numbers in scientific notation and also work backwards and rewrite numbers that in scientific notation back in decimal form. So let's have a go at doing this, and we're going to apply these steps here. Now, there's a few steps I have here. Writing numbers using scientific notation. When we are writing numbers in scientific notation, what we want to do is a few steps here. So first, find the first non-zero digit. So what we're going to do is we're going to read the number from left to right, and we're going to find the first digit which isn't a zero, starting from the left to the right. So just like I did over here with those numbers, I found the first digit which wasn't a zero. And then what we're going to do is place a decimal point after that number. Place a decimal point after that number. So here for my first example, I did 3 and I put a dot. And so I went 3.8214. For the second one, because it's just one number by itself, we don't actually need to worry about that too much. Or you could just do 2.0 if the case that there is no numbers after. Then we want to write all the numbers after that digit until you reach only 0. So we keep writing all the numbers until we reach a 0. So once we hit a 0, we stop. So that's why here I stopped at the 4. For the other example, we don't have any digits after, so I stopped right there. Then we count how many decimal points we've been moved from the original decimal point. Now here we want to look for where the original decimal point here is. For my first example, it was here all the way at the right after that last 0 here. And for this example, it was because it's a small number, it's right here where that decimal point is given. And so we just count how many decimal points we need to move. Then if we moved it to the left, that means it's a positive power of 10, or it's a big number. Or if we moved it to the right, it's a negative power of 10, or it's a small number. The other way that you can see this is if it's a big number, there isn't any decimal points there. If it's a small number, it's just going to be like 0.000, something like that. Okay, let's have a go at a couple of examples of this. So, first example here. Let's have a look at these examples. Write the following numbers in scientific notation. So here we've got 4,500,000. Now what we want to do is we want to write this in scientific notation. First step, we're going to read from left to right of the number and find the first non-zero digit. So if I read from left to right, the first non-zero digit just happens to be this 4. Great. Okay, that's the first step. So find the first non-zero digit. I found it. Then we're going to place a decimal point after that number. So here I would put that decimal point there, and then write all the digits that write all the numbers that are in the digit after you've until you only reach 0. So if I keep reading after that number, the next digit is a 5, which is great. I want that 5, but the next number after that is a 0. So I can just stop it there. So here, when I'm writing this in scientific notation, I'm just going to write 4.5. That's the first part. So that's a measurement part. That's the A value I want in my, if you remember from that definition of scientific notation, that's the A part here. Okay. Then I need to count how many decimal points have been moved from the original decimal point. Now notice here, the original decimal point would be all the way here on the right. Because it's a large number, it's going to be all the way on the right here. And so all I need to do is just count how many decimal points I've removed. I've removed 1 here, 2, 3, 4, 5, 6 to get to this new decimal point that I put in. So what this means is that it tells me that I need to write this as times 10 to the power 6, and because I'm moving it to the left, it's a positive power, and so I don't need to do anything with this number. So here, writing this number in scientific notation, this just becomes 4.5 times 10 to the power 6. Okay, let's have a look at the next example. Next example, we've got 0.00004. Okay, finally got that right. Okay, what we're going to do, same steps as before. We're going to start reading from left to right, and we're going to find the first non-zero, the first digit which isn't a 0. Now, if you read from left to right, the first number which is not a 0, it just happens to be the 4 at the very end. And so what we're going to do, we've identified the first non-zero digit. What we're going to do is going to put a decimal point after that. Then we're going to count all the numbers after that digit until we reach only zeros. Now, because this is the last digit in my number, that means that all the digits after that would technically be a 0. So that means I just stop it there. So for this one, I can just write this as 4. Okay, now that I've done that, I'm just going to count how many times I need to move from my original decimal point. Now, the original decimal point is over here, all the way to this new decimal point. So I'm going to count 1, 2, 3, 4, 5, 6, 7, 7. So that means that I need to times this by 10 to the power. Now, because I moved it to the right, and notice it's a small number, that means I need to have a negative power of 10. So here, this is going to be times 10 to the power negative 7. And so this number here, 0.000004, that's just going to be 4 times 10 to the power negative 7. So that's how we write numbers in scientific notation. What we want to do is we want to find that we first start off by going from left to right, and we find the first non-zero digit. After that, we put a decimal point after it, and then we include all the digits after that point until we reach zeros. And this actually, by doing these first 3 steps, we actually figure out what the value of A is in my scientific notation here. Then from there, in step 4, we count how many times we have to move the original decimal point to our new decimal point. And so by doing this, we find the value of m, the power of 10 that we need to have. And so the other thing that we need to note is if we move it to the left, like we did in that first example, it's a positive power of 10. So like here. And if we move it to the right, it's a negative power of 10. So if you have a look at over here, we had to include that negative sign. Okay, so that's how we write numbers in scientific notation. Now, the other thing that we need to be able to do is work backwards and actually write numbers that are in scientific notation back in decimal form. And so the way that we do this is, first of all, we actually use the steps in reverse. Now, what I do is I first identify the power of 10. So have a look at your power of 10 in your, the index of the 10 in your scientific notation. Then what we do is we move the decimal point. So we look at where the decimal point is in our A, and if we move it, if it's a positive power of 10, we move it to the right. And if it's a negative power of 10, we move it to the left. So if you think about it this way, positive just means it's a big number. So if it's a big number, I need to move it further, make it bigger and bigger and bigger. Negative means it's a small number. So I need to make it small and smaller and smaller and smaller. So, so after I've done that, write zeros above for every digit without a number above it. Okay, so let's have a go at these examples. So let's have a go here. Expressed of each of the numbers in decimal form. The first one, I've got 9.34 times 10 to the power 5. Now, first of all, what I'm going to do is I'm going to find the power of 10. Now, the power of 10 is just here, 5. Now, is that a big number or a small number? Well, because it is bigger than, because it's a positive number, it's going to be big. So that means I need to move my decimal point to the right. And here, this power 5 just tells me I need to move it to the right 5 times. So what I'm going to do is I'm just going to write this number. I'm going to write here 9.34. I'm just going to move that decimal point to the right 5 times. So I'm going to go move the decimal point over here from here 1, 2, 3, 4, 5. Now notice there's a whole bunch of these loops that don't have any digits above it. So what I've written here is if I see one of those loops without a 0 above it, that just tells me I need to put a 0, without a number above it, I just need to put a 0. So what this means is I need to go, okay, this is 0, 0, 0, 0. And so the final number just becomes 934,000 or 934,000. So when I'm writing numbers back in decimal form, all I need to do is identify the power of 10 and then move it either left or right depending on if it's positive or negative. And whenever I see one of those loops without a number above it, I just write a 0. Okay, let's have a go at the next example. Here, this example, we've got 4.71 times 10 to the power negative 5. Now, because it's a negative power of 10, that means it's a small number, which means I need to move the decimal point to the left. So what I'm going to do is I'm going to write this 4.71 and I'm going to move it to the right a bit just so I can get a bit of space so I can move it to the left. And so my power of 10 was negative 5. And so I'm going to move it 5 times to the left this time. So I'm going to move my decimal point. So 1, 2, 3, 4, 5. And so that means I move my decimal point here. And like I said, whenever you see one of those loops, I'm just going to write a 0, 0, 0, 0, 0 above those loops. And so my answer is going to be 0.000471. Now with small numbers, we don't actually just write it as 0.000471. What I need to actually do is I need to include an extra 0 here, right before that decimal point, just to indicate that it is a decimal here. So when you have those negative powers, just make sure you include that 0 in front of that point, that decimal point as well. So that's it for today's lesson. Let's just do a quick recap of what we've looked at in today's lesson. In today's lesson, we talked about scientific notation. We talked about how scientific notation is used to write very, very large numbers and also very, very small numbers. And so here, scientists and mathematicians use it to help us shorthand very large numbers and very small numbers. And the way we do this is we write it in this form: a times 10 to the power m. A is our measurement, and it's a number between 1 and 10. And m is the value, is the magnitude or power of 10. And so if it's a positive number, it means we have a big, it's a large value. And if it's a negative number, it means we have a small value. And so here, the way we worked through how to actually write numbers in scientific notation. So what we did was we looked at a number and we wrote, we found the first non-zero digit starting from the left going to the right, and we wrote a decimal point after it. And then we wrote all the digits after that. And then we just figured out how many decimal points we have to move to get from our original decimal point to that new decimal point. Then we also did the same when we were working backwards to write numbers in scientific notation back into decimal form. So that's it for today's lesson. Hopefully this all helped, and if you have any questions, feel free to email me or send me a message via Google Classroom. I'm more than happy to try and answer your questions. But until next lesson, Year 9s, I hope you guys are staying safe wherever you are, and I'll see you in the next video. Bye!